In this video, we're going to talk about finding PDFs of several independent random variables and applying those PDFs to answer some questions. So we've already talked about this, but to just generalize it more, if we have n different random variables, independent random variables, x1 through xn, we can find the joint PDF of these random variables just by multiplying the PDFs together. So in symbols, this is what we have here, which is the product of the PDFs. So let's say we would have an example here with a random sample. So whenever we have a random sample, we mean that we're drawing the x1, x2, x3 from the same distribution independently. All of them have an exponential distribution with mean 3. Let's find out the probability that all of these have observations have a value greater than 4. So one way to set this up, of course, is just to do the triple integral. We would have our f of x1 times our f of x2 times our, f of x1, x of x2, f of x3 here with respect, and integrate it from 4 to infinity for each of the variables and integrate each of those. That's one way we could do this. Of course, now we can rewrite those integrals. Since it's all independent, we can break it up into 3 separate pieces. Those pieces are just the probability that each one is greater than 4. And then we can cube each of these. This is the probability that x is greater than 4. Since they all have identical distributions, this is the same thing as saying that some x with an exponential distribution x is greater than 4. Same here, same here. So I might as well just say that we have the probability that x is greater than 4 cubed. So if I want the probability that all 3 of these observations is greater than 4, then we would do 1 minus f of 4. In this case, that whole thing should be cubed. There, we should have a cubed around that whole thing, which is what I have here. So we would have e to the 4/3, because that would be the distribution evaluated at 4/3 and then subtracted from 1. And so we just get e to the 4th in this case. So let's extend this to expected values. So let's say that we have y is a product of functions of each of these independent random variables, rather than just some function of the random variables themselves. We say we have a product of the individual functions of the variables multiplied together. So if we want the expected value, then to calculate the expected value, of course, we would do the number of integrals that we'd need over the support of the functions times the PDFs. So this is just rewriting that function in that way. Just like we did in the previous example, we can, since everything here is already broken apart and everything is independent, this space must be, well, we would usually say rectangular, but we'd be in whatever n-dimensional space, whatever that kind of box rectangle looks like. We can break it up into pieces like this with your integrals, and then of course each of these now represent the expected value of the respective variables. So using this idea, if we have independent random variables with means mean 1 through mean n, and then variances sigma squared sub 1 all the way to sigma squared sub n, let's say we have this as our distribution, the sum of the a sub i's times x sub I, then we can figure out what the mean is and what the variance is for that particular distribution. So here, let's say we have the we'll just calculate the expected value of y. That will be your mean for y. Certainly, that's just the expected value of the sum of those things. Expected value behaves nicely with respect to sums and constant multiples. And then we can replace the expected value of x sub I with mu sub I. So that gets us our first part. Let's do this now with our second part. This is the definition of variance, right? You do the expected value of y minus mu sub y squared. So now we're just plugging in the pieces that we know. This is how y was defined. This is what we just found in the previous part. This is just rewriting the sum, right? Because I can, we got a sum here and the sum here going to the same index. And I got the same constant in both of those, so I can just factor out the constant. That's all we're doing there. All right, so now this is, if we look at this, This is a product of two of these things. Now notice I've changed the index, but it's literally the same thing, right? This is just this sum times itself. So this is this sum, and this is just the same sum, just with a different letter. So now, if I think about combining those two things, I get a double sum, where I do the individual product. So I'd have the AI times the AJ, and then I have the x sub I minus mu sub I, x sub j minus mu sub j multiplied together. And now again, we know expected value behaves nicely with respect to sums and constant multiples, so we can pull the expected value all the way in. And now I can break this expected value up over the product if they're independent. Now, they will be independent so long as the I is not equal to the j. If I and j are equal, then I have the same variable, and they are absolutely not independent of one another. So this gives you the expression when I equals j. There are n times that happens, right? I and j can both be 1 or 2 or 3 or all the way up to n. The rest of the time, they're not equal, and so we get this. So, pardon me. Over here now, since they're independent, when I is not equal to j, I can break the expected value up over the product. This isn't changed over here. Now, I break the expected value up over each difference. So we have expected value of x sub I, and then just minus mu sub I, because that is a constant. Same thing with j. But expected value of x sub I and expected value of x sub j are mu sub I and mu sub j respectively. So these are just going to be 0, and you just end up with this piece. But if you look at this summand, this is exactly the variance of x sub I. So, again, if you've got independent random variables, you can find the variance of the sum by doing the sum of the variances. And if you've got constant multiples, you square those. When they're not independent, then the summands in that second sum we just talked about are not equal to 0 anymore, but they are the covariances. That's exactly what the covariances are. So let's look at a particular example. Let's say we have ax plus by here as your z. Here is how we would normally calculate variance. Let's multiply everything out and break up our expectations when we can. So again, here we squared to this line. Here we just broke up the expected value over the sum. And then we did the exact reverse. In the first part, we broke up over the sum with the expected value. Oops, this should be an expected value of y squared here. There should be an expected value around that y squared. Here we squared out. Combined, well, like terms, I suppose. We factored out things that we could. We combined the terms that have a squareds in them, combine the terms that have b squareds in them, and combine the terms that have a 2ab in them. And we notice that we have variance of x in the first term, variance of y in the second term, and covariance of xy in the third term. Notice this kind of looks like a FOIL idea, right? We've got an a squared, a 2ab, and a b squared in there as the different coefficients. So let's look at this example. Let's say we have independent random variables. These are the means and the variances. And it says, what's the mean and variance of z? Well, the mean is easy, right? We do the linear combination that we are given for the means that we are also given. So we do 3 times the mean for x, negative 2 times the mean for y. Add them together, get 24. The variance you do is something similar. They're independent, so I don't have to worry about the covariance piece. But remember, we have to square the individual coefficients in this case. So we square the 3. We square the negative 2. That's important. We don't want to subtract variances here. We're always going to add variances. So now we get 9 times 7, 4 times 13, which gives us 115. What would happen if the covariance is negative 4, though, instead of being independent? Well, the mean doesn't change. Whether or not they're independent does not affect what the mean is. it does affect what the variance is. So if the covariance is -4, we go back to that original problem. It's a squared, which is 3 squared, -2 squared, that's your b squared. And then it was 2ab, and then covariance of xy. So now your covariance of xy is -4, and if you do all the calculations there, you get 163. So we'll do more examples of these in class, but this should give you a brief idea of where we're headed with the several independent random variable information.